So these pointers and the power that they bring to you, including dynamic memory allocation, is a great thing. It's a fantastic thing. But with power comes great responsibility. Is that the dialogue from some movie? I don't know. I don't care. In case of pointers, I would say with power comes great danger, right? So there are a few dangerous things that can happen with pointers. So we're going to discuss them today. So these are some very frequent issues that one can face while using pointers and dynamic memory allocation. I'll tell you a story, a short story, right? So you can relate these issues with that story. So there was this builder, a very famous builder in a city, right? So he purchased a great land, right? A plot, and he intended to build a housing complex, right? In there. So initially the plan was to have one building here, one building here, one building here, right? One building here, and have common amenities such as swimming pool and gym to have common amenities area, right? So builders build this thing, and he was just about to start building this common amenities, right? Like the park and the swimming pool and everything, right? But the builder got greedy. He was able to sell all these flats even before he started building this common space, right? So he scrapped the plans of building this common amenities here. Instead, he built one more high-story building, one more tower. He was able to sell few more flats, few more profit, few more dollars or rupees or whatever it is. But obviously, the residents who bought apartments in these buildings started complaining. Where is goddamn swimming pool? Where is goddamn gym? Where is our common space? Where is common amenities? So builder thought he could get away with that, but he obviously could not. So now builder had to provide those common amenities. So he could see that there was this, this small piece of land, right, which was lying vacant. There were other housing complex around, right? There was commercial buildings, but this space was vacant, and it seemed like nobody was paying any attention to that. So builder decided to do encroachment, and consider this as his own area, and built the swimming pool and all these things here. So he did that, right? He built a swimming pool and a gym and everything here. Everybody was happy. So one day, one of the residents from this Tower C, right? His name was Monty. So Monty one day decided to inaugurate the swimming pool by himself. And Monty went to the swimming pool, right? Monty removed most of his clothes, except his swimwear, and jumped in the swimming tank. So after a while, Monty did not return to his house. So Monty's girlfriend, soon to be wife, got worried, and she went to the swimming pool to look for Monty. And what does she see? There were no signs of Monty, except she could see his swimwear floating on the water. Where is Monty? So as it turns out, this piece of land which the builder encroached upon belonged to white walkers. It was where white walkers were buried. It was their graveyard. Nobody really knew about it, but it was their own private space where they rested in peace. The white walkers pulled Monty inside, There was the graveyard below the surface of the earth, below the swimming pool. So Monty was now white walker. I'm not kidding you. This is a real story. It happened here, right here, few miles from my residence. So this is what happens when you access the area which is not allocated to you. Anything can happen. It could be a wild pointer. It could be a dangling pointer. It could be an error. It could be anything. It could be segmentation fault. So do not try, even by mistake, to use the area which is not allocated to you. Results are unexpected. So coming back to the programming, why does null pointer assignment error happens? The null pointer assignment error happens when your program tries to access an illegal memory location which is located either in the operating system address space or some other process address space. When your program tries to access a memory location which is not located in your program's memory space. Your program's memory space is this. Again, I repeat, code segment, data segment, stack, heap, and data section. So this is program space. This is memory space, address space for your program. But what if you are trying to access a memory location which is not in this part, which is in somewhere else, either in OS address space or other process address space? Then you will get this null pointer assignment error. One short replication of this is when you do this. Int star p equal to null. In C language, when you assign null to your pointer, this means value is 0. This null value is 0. This 0 location with address 0 is almost always in operating system's address space. And if you try to say now star p equal to some value, let's say 12, right, you will get this null pointer assignment error. Why is this happening? When you say p equal to null, it's a good practice, by the way, to initialize pointer like this with null. But then you'll have to acquire some legitimate memory, like by using p equal to int star malloc. You must acquire legitimate memory, let's say of 20 bytes from your heap before you start using p to store values or to do anything. But you did not do that, and you straight away said p star p equal to 12. So you will get the null pointer assignment error. You can also get null pointer assignment error because of wild pointers. So what is wild pointers? It's a pointer, right? But it's a local variable. We are declaring this in some function, let's say void main or any other function. So this is local variable, and uninitialized local variables contain what? They contain garbage values. So this p could store any garbage address. Now, if that address does not fall in your address space, it does not belong to stack, heap, or data section of your address space. Your, in the sense, your program's address space. That address, that garbage address, let's say 1,348. This is the garbage address now stored by P because you did not initialize it. So this address, if it falls into some other process address space or into operating system address space, then again, if you try to assign star p equal to 12, you will get a null pointer assignment error. So using uninitialized pointers that contain garbage addresses is again a dangerous thing to do. You may land safe. Maybe uninitialized pointer contains a garbage address from your stack or heap, right? Still, it's not advisable to use it. The next thing is dangling pointers. What is dangling pointers? So dangling pointer is a pointer which is storing the address of a memory block which has already been deallocated or freed. So while we are discussing dynamic memory allocation, we talked about functions such as malloc, calloc, and realloc, right? But there was one more function that we should have talked about, but we did not, was free, right? And this requires a starting address. So what does free do is that free's job is when you do malloc, right? Let's say 40, that is you want to allocate 40 bytes of area, right? Malloc finds the 40 bytes of area, let's say starting at location 1000, right? So you will assign this starting address of this dynamically allocated memory block to the p pointer, right? So this is what malloc does. The problem is now you use this block for doing some calculations, so storing some value temporarily. You are done with your calculations, you display your results. Now you don't require this memory block anymore, right? Then it is your duty in your program to code something like this, free p. This function will basically make sure that P still stores this starting address, right? That is 1000. So free P will make sure that it will deallocate whatever dynamically allocate memory, 40 bytes, was allocated starting from 1000. Free P will deallocate that memory so that this memory could be utilized for some other calls of malloc, calloc, or realloc, right? So this is a good practice. When you do not require the dynamically allocated memory anymore, then you should always free it, right? Now, one problem with free is that, let us say you allocated dynamically 40 bytes and stored that starting address 1000 in P. Then you did some processing, right? You wrote some code to use that memory area for storing the values, for displaying, for changing, whatever. And then, right, you decided to use free. So you said free P. So this area, along with your values, right, whatever they were, will be deallocated. That means it will be marked as available for other malloc calls from some other functions or programs or whatever, right? Mostly functions, because this is still in your address space, your program's address space, right? Now, going ahead after this line of code, after this call, if you try to, let's say, access P, or let's say do something like this. Now, what you are doing is you are using a dangling pointer, right? This pointer now has become dangling pointer. Why? It is still storing this address 1000, by the way. At this point, it is still storing the address 1000. But this address space or this block of memory might have been allocated to some other purpose, right? As I said, the boundary between heap and stack is flexible. So stack can take memory from heap if it requires. So it may happen that some other variable from some other function of yours might be using that memory location. P still has the address. It doesn't have the right to use that memory, but it still has the address, right? So if you assign this value to address stored at P, it will change the value, but this might override the value that was intended to store here by some other variable. So this is called as dangling pointer. One more example of dangling pointer is variables to which the pointer is pointing going out of scope. For example, let's say you have one character pointer, star P, right? It is initialized to null initially. Then there's some line of code. There's a block of code where we define a variable x, right, equal to, let's say, small a, right? And you say P equal to address of x, right? But this is a block. And the scope of this local variable is this block. It's a block level variable. So as soon as this block finishes, this variable goes out of scope. Now, at this point onwards, P becomes dangling pointer. Why? Because it was supposed to store address of this variable x, right? But now x is out of scope. It is removed from the stack. There's no more x. The memory location is there, right? The memory location is there, but it is no more accessible by x. But you still have the address. So now this memory location, because it goes out of scope, this memory location can be utilized by the operating system for some other purpose. But because you still think that you're storing the address of x, and you might want to do something like k or something like that, you are trying to access the area which has been deallocated. So this, in this case, P again becomes a dangling pointer, right? This was a block of code, right? This could be a function like, let's say, int star return type fun, right? Now you declare a variable, let's say integer x equal to 5, and then you return address of x, right? You have, let's say, integer star p pointer. You have some code, and then you say p equal to fun. Fun has this local variable x, right? You are returning the address of x. But now, as soon as this function call finishes, right? As soon as this function call finishes, this x goes out of scope. That means the memory given to x is deallocated automatically. You know that, right? But P is still storing the address of that previously allocated memory to x, right? So P is holding on to an address, a memory location, which has been deallocated, and that might be currently be reused by operating system for some other purpose. So here P becomes your dangling pointer. It is pointing to a memory which has already been deallocated or freed. So if you try to say star P equal to 13, you try to access that memory location, this might result into unexpected outcome. You might end up overwriting the value of some other variable, right? Because once this has been deallocated, once this call is done, this is deallocated. This memory could be reused either again by stack, or even heap could use that memory location if required for some other purpose, right? So that's one more example of dangling pointer. Here we could avoid for P to become dangling pointer by making this variable as static, right? If you make this static, the scope of this variable is throughout the program, not just limited to this function. That means this variable will outlive this function call, and in that case P won't become dangling pointer after this function call. It will become a legitimate pointer pointing to X, which is a static now. So that is one solution. But keep in mind, dangling pointers or wild pointers, they may give you unexpected outcome, unexpected output, as well as runtime exceptions or errors, which you don't want. Right? I often compare dangling pointers to dangling lovers. There was this girl, Geeta. She used to live in block A, right? Geeta had a boyfriend, Sham. Sham used to really adore, love Geeta, used to go to her place outside her gate, basically just to get a glimpse of Geeta. So Sham had the address of Geeta, right? Now what happened is that Sham had a terrible accident and Sham went to coma. Geeta defied her family, went to see Sham, prayed for Sham, hoped that Sham will come back to senses. But no, days, months, years passed, but Sham continued to remain in coma. After a point, Geeta lost hope and Geeta decided to go with Ram to United States, right? So now Geeta no more lived in block A. She relocated. Her flat was deallocated. She was relocated. Now this block A was allocated to another girl called as Sita. Now as it happens, after some years, suddenly one day, a miracle happens and Sham comes out of coma. Now Sham's last memory. So first thing that Sham does after coming back from coma is to go to block A, the address, right? He tries to access the value at that address. That is now Sita. But there's a problem because Sham cannot differentiate between Sita and Geeta. Sham thinks Sita is Geeta and chaos. So it's similar to that. Unexpected things can happen when you have dangling pointers or dangling lovers. So it's best to avoid both of them. The last issue that can happen with improper use of pointers and dynamic memory allocation is memory leakage. Memory leakage happens when you forget to call free. Free is used to deallocate dynamically allocated memory, right? Now, for example, let's say we needed a function called as array work. So we had some array related work like inputting a particular array, doing some arithmetics and displaying the array, and that's it. That was the job of this function, right? So let's say we created a pointer. We wanted to create dynamic array. So we said p equal to, int star malloc, and let's say some size. I'll just assume it's 400 bytes. And then we did some functionality. We wrote some functionality here to input the array and do some arithmetic, display the array, right? And we are done. We were done with everything here in itself. Now, in the void main, we had lots of other code, right? So there was one call here, right? Let's give it a size, integer n. And we'll say size of int into n, right? And then we had another call to array work for, let's say, 550, right? And then another call to array work for, let's say, 450. We are going to need this functionality few times in our main program, right? Now, the one thing that we did not do here after we are done with using this dynamic array, that we forgot to add this line, right? Now, the problem is that this function allocates memory to a local pointer, right? This pointer is local to this function. When you do not write free and you allocate memory for whatever amount of bytes, right? That memory block will remain allocated. Operating system will not know that that area from memory can now be allocated to some other call, some other function, right? So as soon as you exit this function and continue your execution, right, this area of memory remain allocated to the previous call. And now, furthermore, because this pointer was local to the function, we don't have access to that starting address of that dynamically allocated memory block. So even though it is still allocated, we have no way to use it because we lost the starting address. As soon as this function call ended, this variable was lost out of scope. So we lost the starting address. So that memory block remains allocated and we don't have starting address. That means it's a leakage. That memory block is unusable. So this is called as memory leakage. And if you are making the call to this kind of function without free, let's say 5 to 6 times, every time you are causing that memory leakage. And it depends on what's the size of array you want to create in each call. So imagine how much memory leakage you are causing just because you forgot to call free, right? So important thing is to avoid memory leakage is that if you're done with the use of dynamically allocated memory, you no more require it. At that point itself, you should deallocate by explicitly calling the function free. These are certain things you must keep in mind while using pointers and dynamic memory allocation.